Welcome to the deep dive. Today, we're tackling something, well, huge. The scope makes long-term climate projections look like planning a weekend away.
It really does.
We're diving into a document that thinks in centuries, not, quarterly
Right.
earnings.
Forget election cycles.
Our mission today is to unpack the Stellar Advancement Protocol V6.0. It's this radical open source plan, essentially an operational manual.
And the goal. Pretty
To
ambitious.
say the least. It's designed to accelerate humanity's jump from where we are now, a Type 0 civilization basically stuck on one planet.
To a Type 2 civilization, one that can actually harness the power of our entire star.
So not just solar panels on roofs.
No, we're talking the whole star. And look, this isn't just some sci-fi dream on paper. It's laid out as a detailed plan. The core idea is solving global scarcity permanently.
Permanently. Wow.
And to really get why this protocol even exists, you kind of have to understand the founder's motivation. It's this interesting mix of high-level economics and deep human psychology.
Okay, I definitely want to dig into that connection because economics and psychology, they seem worlds apart sometimes.
They do, but here they mesh. It stems from Dr. Pippa Malmgren's work, observing that we're right on the edge of these huge sector-spanning breakthroughs. We're like stuck at the finish line.
Just about to make the leap, but not quite getting there.
Exactly. And connecting that observation to the very stark numbers of the Kardashev scale, the big realization was the breakthroughs are already out there. Sayad Potter Plan, scattered, but they're isolated,
Locked away.
locked away.
Yeah.
And that isolation the founder saw isn't just institutional, it's fundamentally a cognitive problem. It mirrors how our own brains work, or sometimes how they don't work together effectively.
And that brings us to the brain analogy you mentioned earlier, the corpus callosum idea.
Precisely. The source material leans heavily on the human brain as its core metaphor. We know that extraordinary genius, like Einstein's, seems linked physically to an unusually dense corpus callosum.
That's the bit connecting the two halves of the brain, right?
Right, that thick bundle of nerves.
Right.
Einstein wasn't just crunching numbers in isolation in his, say, left brain. He was connecting that abstract math with really radical visualization, probably more right brain stuff. Imagining riding alongside a beam of light, that kind of thing.
So it was the connection between the logical and the intuitive, the visual.
Absolutely. And the protocol's argument is that humanity, collectively, has developed these incredibly powerful, specialized knowledge hemispheres. You got the physicists over here, the chemists there, the industrial welders, the biologists.
All experts in their own domain.
Super specialized.
Yeah.
But we lack that crucial connective tissue, that corpus callosum for humanity.
So the knowledge is there, but it can't flow between the different areas.
Exactly. We have immense power, but it's locked in silos. Think proprietary IP, academic paywalls. But maybe the biggest barrier of all is just specialized technical jargon. Nobody understands each other's language.
Okay.
So the protocol aims to be that collective open source corpus callosum, the bridge that systematically connects all these isolated pockets of knowledge.
Making those aha moments almost inevitable, rather than just happy accidents.
That's the goal. Turn accidental discovery into a pipeline.
So our mission for you, listening in, is to really grasp the mechanics of how this radical approach is supposed to work. It's not about inventing brand new physics from scratch.
Not at all.
It's about speeding up and connecting the breakthroughs that the document argues already exist. They're just trapped behind these walls of specialization.
And the driving question behind it all is almost, existential, isn't it? Why did we stop dreaming big after, say, the moon landing in '69?
Yeah, what happened?
Why did we seem to trade that focus on, reaching for the stars, for the tyranny of the 90-day earnings report? And more importantly, how do we build the connections needed to finally systematically end resource scarcity forever?
That is a heck of a starting point. Okay, let's define the destination first, type 2. So we're aiming for type 2 status on this Kardashev scale. Now, for someone who's maybe pretty informed but doesn't track macroastrophysics daily, what does a type 2 civilization actually look like, practically speaking?
Right. So type 2, at its heart, is all about energy mastery. It means a civilization that can capture and use 100% of the energy output of its home soil.
100%? That sounds immense.
It is. Think truly colossal engineering. The classic example is something like a Dyson swarm, not necessarily a solid shell, but vast clouds of orbiting solar collectors, maybe between Earth and the sun, just constantly soaking up the sun's full power output and beaming it back or using it out there.
Okay, and when you frame it like that, it really highlights how little energy we actually use now. Where does the protocol say humanity is currently?
We're pegged at about type 0.73. Now, 0.73 sounds, pretty far along maybe.
Yeah, over halfway to type 1.
You'd think, but the number hides the real story. The underlying stat is that we currently utilize, get this, 0.0000005% of the sun's total energy output.
0 point. How many zeros was that?
5 zeros after the decimal point. So 45 billionths of a percent. Less than 1/1,000,000th of 1%.
Wow, okay. That's humbling.
Isn't it?
Okay,
It's
yeah.
a really visceral reminder of just how limited we are right now. We're still basically just scratching the surface of our own planet's resources, fundamentally constrained by energy and the infrastructure to use it.
And the implications of actually reaching type 2, they go way beyond just having cheap electricity, don't they? It sort of redefines humanity's future.
Oh, absolutely. It fundamentally changes the game. Becoming type 2 means statistically becoming a civilization that essentially can't go extinct.
Because we wouldn't have all our eggs in one basket, planetarily speaking.
Exactly. Your population, your resources, your knowledge would be spread across multiple worlds, multiple habitats within the solar system. You'd have access to functionally limitless energy, limitless resources.
Which unlocks, oh, almost anything.
Exponential potential. Room for trillions of people to flourish, not just scrape by. Scarcity, the thing that has driven almost all of human history, conflict, economics,
Yeah.
it becomes optional, something you read about in history books.
But the flip side is the cost of not getting there. If we delay this or fail, the protocol puts a number on that, a human cost.
It does, and it's frankly brutal. The document is really clear. Every single day we delay hitting type 2 capabilities costs humanity, they estimate, around 200,000 person-years of unnecessary scarcity.
200,000 person years per day.
Per day. Lost potential, lost flourishing. And the direct human toll is just staggering. Every year of delay means roughly 2.8 million preventable deaths.
Preventable deaths linked to what?
Directly linked to energy poverty, resource conflicts driven by scarcity, lack of basic infrastructure like clean water or sanitation, which needs energy. All the downstream effects of not having enough power and resources distributed properly. So chasing type 2 isn't just some grand technological ambition.
It's framed as a moral imperative. Okay, so that leads us to maybe the biggest structural hurdle identified in the protocol. And it's not a physics problem, surprisingly. It's about time. The temporal mismatch bottleneck.
Yes, this is key.
We're trying to pull off a project that needs maybe centuries, millennia of continuous effort.
Using systems designed for quarterly results,
Right. It seems fundamentally misaligned.
the protocol argues that the real enemy isn't the difficulty of fusion or material science. It's our broken clock. Our planning horizons are structurally, almost chemically, unable to cope with this timescale.
So lay out the different clocks we're running on.
Okay, look around. Corporations, they optimize for quarterly earnings. That's 90-day thinking, Max.
Right. Wall Street demands it.
Governments,
Yeah.
they plan in election cycles. Maybe 4 years if you're lucky, often less.
Chasing the next vote.
Academia,
Yeah.
often driven by annual grant cycles. 1-year thinking. Even individuals, when we plan for the long term, what do we think about? Retirement.
Yeah, maybe 30, 40 years out if you're
Yeah.
diligent.
Exactly. 40-year thinking is about the max for most institutional or personal planning. None of these timescales can sustain the focus, the investment, the institutional memory needed for something that takes multiple generations.
But hang on, humanity has done long-term projects before, right? Things that span generations. The protocol mentions some historical examples.
It does, and leverages them as proof of concept. Proof that we can think and act long-term if the conditions are right. Think about the great medieval cathedrals in Europe.
Like Cologne Cathedral.
Cologne is a prime example. Took 632 years to finish. Imagine that. That vision survived dozens of kings, wars, plagues, economic collapses. But the work continued.
How? What kept it going?
An incredibly powerful shared vision, a sense of building something transcendent for God, for the community, that were way beyond individual lifetimes or economic gain. And institutional structures like the guilds that preserve the knowledge and the drive.
Okay, what else?
Think about the Dutch polders. Reclaiming land from the sea. That wasn't a one-off project. It required centuries of continuous, coordinated engineering, dike building, pumping, maintenance, generation after generation working together against the water.
A constant shared effort against a common challenge.
Precisely. And maybe the most stunning example of pure knowledge transfer across time is Japan's Ai's Grand Shrine.
The one they rebuild.
Exactly. It's been meticulously dismantled and rebuilt identically every 20 years for the last 1,300 years.
1,300 years, that's mind-blowing. How many generations?
About 65 successive generations of master carpenters and artisans have passed down these incredibly complex techniques. The point wasn't just the building. It was the process of rebuilding as a way to keep the knowledge alive, perfectly preserved through active transmission.
So looking at those examples, cathedrals, polders, Ai Shrine, what are the common threads? What made them succeed where, say, a 50-year infrastructure project today often fails?
The protocol pulls out three key factors that it tries to replicate. First, like we said, a shared, almost sacred vision. Something bigger than quarterly profits or election wins.
Oh, why that lasts?
Exactly. Second, a really effective way to preserve and transfer knowledge. The ice shrine's ritualized rebuilding is maybe the ultimate example, ensuring the masters had to teach the apprentices every 2 decades.
Active knowledge transfer, not just writing it down.
Right. And third, institutional continuity. Structures, whether religious orders, guilds, or specific community trusts, that are insulated from the day-to-day churn of politics and economics. They provide stability over centuries. We need to figure out how to build the modern, maybe digital equivalent of that persistence, likely using global open source coordination. Okay, so if the timeline mismatch is the big structural challenge, the protocol argues the biggest immediate bottleneck, the thing stopping breakthroughs right now, is actually simpler. It's knowledge segregation.
Right, the prison of jargon metaphor you mentioned, that really resonated. It makes experts in one field practically blind to solutions sitting right next door in another field just because they speak different technical languages.
That's the core thesis. Humanity isn't really suffering from a lack of knowledge overall. We're suffering from a catastrophic failure of communication between knowledge centers.
And the example they use is the fusion researcher and the welder.
Yeah, it's the perfect illustration. You've got a top-tier fusion scientist, brilliant person. They're stuck on how to contain this incredibly hot, unstable plasma. It involves extreme heat, intense magnetic fields, materials under immense stress.
A classic frontier physics problem.
Right. Now, the answer, or maybe a critical piece of the answer, might lie in a technique used by, say, an industrial welder who joins exotic metals for deep-sea oil rigs, or maybe in a manual for high-frequency induction furnace maintenance. That welder deals with plasma arcs, extreme temperatures, material reactions under pressure every single day.
But they speak different languages.
Completely. The researcher talks about magnetohydrodynamics and plasma instabilities. The welder talks about amperage, slag inclusions, and heat-affected zones. They could be describing analogous phenomena, but the vocabulary is an impassable wall.
Hang on, though. Isn't there a real risk here? If you try to translate something super complex like optimizing plasma confinement using magnetic shear fields into just, I don't know, how to stop hot stuff from spraying out, aren't you losing all the crucial detail? The nuance that only the PhD really gets?
That's a really important question, and the protocol addresses it directly. The goal isn't to replace the PhD or dumb down the science. It's about translating the problem into a recognizable, generalized pattern.
So focus on the shape of the problem, not the deep physics initially.
Exactly. What does this problem look like functionally?
Yeah,
What is it doing? The deep nuance is absolutely essential for validating a potential solution later on. But the initial connection, the spark of, hey, that looks like something I deal with, often comes from seeing that simplified, analogous pattern.
And the protocol argues that history is just full of examples proving this works, that big breakthroughs almost never come from just digging deeper in the same hole.
Almost never. They happen when someone connects two seemingly unrelated ideas.
Like the microwave oven.
Perfect example. Not invented by a chef or a food scientist trying to cook faster. It came from Percy Spencer, an engineer at Raytheon working on radar technology during World War II.
Military tech.
Right. He was testing a magnetron, this device that generates the microwaves for radar sets, and he noticed the chocolate bar in his pocket started melting.
Whoops.
Right. But instead of just thinking, weird, he made the connection. These radar waves, military application, can heat things up. Kitchen application. Boom. Microwave oven.
Okay, another one.
Heart stents saved countless lives. The breakthrough didn't come from just refining existing surgical tools. Dr. Julio Palmaz, a cardiologist, got frustrated with limitations. He looked completely outside medicine.
Where did he look?
Automotive fuel injectors. He realized the core problem wasn't just the stent material. It was how to get into tiny twisting blood vessels and then expand it reliably. Mechanics of a fuel injector gave him the idea for the balloon expandable delivery system, connection across fields. And
Amazing.
the really simple one? Velcro. George de Mistral, a Swiss engineer, goes for a walk with his dog, comes back, dog's covered in burrs.
Oh,
Annoying, right?
happens all the time.
But instead of just pulling them off, he got curious. Put one under a microscope, saw the tiny hooks on the burr and the loops in the dog's fur. He connected that simple, natural fastening mechanism to a potential industrial application. Hooks and loops, Velcro.
So breakthroughs often hinge on these accidental moments. A chance observation, a random connection.
Until now, yes.
Hmm.
It's been like winning the lottery. Maybe you have the right conversation at a conference. Maybe you read an article in a totally different field. Maybe your chocolate bar melts.
So the goal of the Cellar Advancement Protocol is basically to stop relying on luck.
Precisely. To take that accidental discovery lottery and turn it into a systematic high-throughput pipeline. Make those connections happen on purpose, at scale.
Accelerate the accidents,
You
essentially.
got it. We want to be breakthrough discovery feel more like a manufacturing process. And the potential payoff is enormous. The document makes this powerful economic case. Just one single connection. Imagine that welder's insight solving a core fusion containment problem that could realistically cut the timeline to commercial fusion power by decades.
Decades.
Yeah, you take a, say, $10 billion physics problem and find a key piece of the solution from maybe $50,000 worth of existing industrial knowledge that just needed connecting. That kind of time compression applied across all the necessary technologies for Type 2. That's the ultimate ROI.
And the protocol actually outlines specific targets, examples of what these connections could unlock.
Yes, it focuses on high-leverage connections where a breakthrough would cascade. We mentioned welding and fusion. If you connect deep knowledge about stabilizing high-energy welding arcs to the physics of plasma containment.
You might solve the keeping it stable problem.
Right. The protocol suggests that could potentially lead to sustained fusion reactions, maybe net energy gain within 5 years, instead of the 50 years people often talk about. That means the first commercial fusion reactor could potentially come online within a decade or so. Game changer for energy.
Okay, what about managing the complexity? A Type 2 civilization would have unbelievable infrastructure.
Huge complexity.
Yeah.
Think managing a Dyson swarm, millions or billions of independent orbiting collectors. How do you coordinate that?
Sounds impossible.
Well, the protocol suggests connecting it to online gaming.
Gaming? Seriously?
Seriously. Think about massive multiplayer online games, MMOs. Their core architecture is designed to handle potentially millions of players, all acting independently in real time, within a single persistent virtual world. That coordination challenge is structurally very similar to managing a vast swarm of satellites or energy collectors.
Using MMO architecture for Dyson swarm management. That's lateral thinking.
It is. And then there's material science. Things like building a space elevator.
Yeah.
We just can't do it with current material.
They're not strong enough, right?
Not nearly strong enough, especially over those distances. The cable would snap under its own weight. The required leap here involves connecting biology, specifically how biological systems repair themselves, like DNA repair mechanisms.
Self-healing.
Exactly. Connecting that concept to advanced materials. Imagine carbon nanotubes that can detect and repair microfractures, inspired by how DNA works. That kind of self-healing property might be the key to finally achieving the incredible tensile strength needed for a space elevator cable.
Again, the barrier isn't necessarily inventing something brand new from nothing.
It's connecting existing knowledge DNA repair, nanotubes in a new way.
Precisely. It's coordination and communication. So to build this engine that systematically generates these connections, the protocol needed a model, a proven way to scale up complex expertise distribution. And they found it in a really unexpected place.
Not physics labs or engineering firms. Nope. Medical innovation. Specifically, the Aravind Eye Hospital system in India.
Okay, I have to admit, linking high-volume cataract surgery to building a Type 2 civilization, that sounds like a stretch. What's the connection?
It sounds odd, I know. But the organizational insight Aravind developed is genuinely revolutionary and directly applicable. Aravind performs more cataract surgeries than basically anyone else on the planet.
Okay, high volume.
But here's the thing. They didn't achieve that volume by inventing some radical new surgical laser or anything. They did it through organizational science, process innovation.
Oh.
They fundamentally rethought workflow. They realized that even a complex procedure like cataract surgery could be broken down into many smaller, discrete, repeatable tasks. And crucially, not every task requires a highly trained, expensive surgeon.
Ah, so they use division of labor intensely.
Exactly. They systematically train other people, often local women with maybe no prior medical background, to handle specific critical but non-surgical steps with extreme proficiency.
Like what kind of steps?
Things like taking preoperative measurements, ensuring perfect sterilization, managing patient flow, administering eye drops correctly, post-operative checks, preparing the next patient. All the stuff around the core surgical moment.
So they free up the surgeon to just do the surgery.
Precisely. By delegating maybe 80% of the total procedural time and tasks, the handful of highly skilled surgeons can focus exclusively on the most complex part. Removing the cataract, inserting the new lens, just that core minute or two.
And the result is that incredible efficiency number.
Right. They can achieve something like 6 to 8 operations per hour per surgeon. The typical rate in many Western hospitals might be 1, maybe 2 per hour.
So 4 to 8 times faster just through better organization and delegation?
Exactly. It's an exponential leap achieved purely through optimizing the process, not just the core technology. And that is the principle the protocol applies to scientific discovery.
Okay, I see the link now. Complex knowledge work, like scientific breakthroughs, can also be broken down.
It can. You don't necessarily need a Nobel laureate physicist involved in every single step of finding the next physics breakthrough. You need people specifically trained to do certain parts of the process, like spotting patterns or translating concepts.
Which leads directly to this idea of the pattern recognition core. Not specialists in the traditional sense, but what do they call them? PRAs?
Pattern recognition assistants, yes. They are the trained generalists, the connectors. A PRA isn't expected to understand the deep quantum physics behind fusion or the exact chemical reactions in a new battery.
What is their job then?
Their job is laser-focused on recognizing what a problem looks like structurally, visually, functionally. They spot that a heat dissipation problem in a new microchip design looks remarkably similar to a cooling problem in a jet engine turbine blade, even though the underlying physics and scales are totally different.
They see the analogy, the pattern.
They see the pattern. And their training allows them to describe that pattern in a generalized way that someone in the other field can understand. This makes that crucial first step, making the connection accessible to potentially thousands of trained people worldwide, not just the handful of experts at the top.
Okay, and to make this manageable, the protocol splits this pattern recognition core into different specializations, right? Based on fundamental principles.
Correct. You can't just have everyone looking everywhere. You need some focus. So they've defined 5 core specialization areas for the PR core based on really fundamental physical concepts.
What's the first one?
First is heat and energy. This group focuses entirely on connecting problems related to managing thermal energy, especially at extremes.
So linking things like.
Linking challenges in, say, industrial welding, where you're dealing with intense, localized heat, maybe specialized 3D metal printing, which relies on precise melting and cooling, advanced cooking techniques like sous vide or molecular gastronomy, which are all about heat control.
Okay, wait. Cooking and fusion, how does that connect?
Think about it structurally. Managing the incredibly rapid heat fluctuations and achieving stable temperatures in a fusion plasma, fundamentally that involves principles of heat transfer, thermal equilibrium, preventing hot spots. These are the same kinds of problems, just at vastly different scales and energies that a high-end chef deals with using precise temperature control or a metallurgist deals with in heat-treating alloys.
It's about the pattern of heat management, not the specific application.
Exactly. They exist in totally separate worlds, different jargon, but the underlying shape of the heat problem might be analogous.
Okay. Second specialization.
Pressure and flow. This core links insights across anything involving moving fluids, gases, or even plasma under pressure, and dealing with things like turbulence and flow control.
So hydraulics.
Hydraulics, definitely. Aerodynamics, how air flows over a wing. Plasma physics, how that hot gas moves inside a reactor. Even deep ocean engineering, managing pressure in pipelines thousands of feet down.
Give me an example connection there.
Okay, imagine a deep-sea drilling company has developed incredibly clever ways to manage sudden, unpredictable pressure surges in their pipelines to prevent blowouts. That technique, translated, might offer a new way for a plasma physicist to think about controlling sudden instabilities or turbulence in their fusion reactor. Same physics problem, managing unstable flow under pressure, just wildly different context.
Got it. Third area.
Materials and structure. This one is absolutely critical, especially for building anything big in space, like elevators or habitats.
This bridges things like construction and biology.
Yes, construction, biology, think bone structure, spider silk, nanotechnology, and large-scale space engineering. The protocol explicitly pushes for matching bio-inspired mechanisms, how nature builds strong, lightweight, resilient structures, to developing new industrial materials.
And this is where that specific number came up earlier, the carbon nanotube strength.
Right. The key target here is achieving carbon nanotubes or some similar material with a tensile strength consistently over 63 gigapascals. At scale.
Okay, remind me again, 63 GPa. Put that in perspective. How strong is that?
It's ridiculously strong. Gigapascals, GPa, measured tensile strength, how much pulling force something can take before it snaps. 63 GPa. It means a cable, just the thickness of a standard pencil, could theoretically support the weight of around 150 average cars.
150 cars
Yeah.
from a pencil-thick cable.
Roughly, yeah. It's about 100 times stronger than the best structural steel we use today in bridges and skyscrapers. You need that kind of insane strength-to-weight ratio for something like a space elevator cable, just so the cable itself doesn't break under its own enormous weight stretching tens of thousands of kilometers into space.
So the PR core for materials and structure is hunting for clues in nature or maybe obscure industrial processes to figure out how to actually make stuff that strong, reliably, and affordably.
That's their mission. Find a blueprint. Okay, fourth specialization,
Go ahead.
control and coordination. This is all about managing complex, decentralized systems.
It's like the MMO example for the Dyson Swarm.
Exactly like that. This core unites insights from gaming architecture, high-level military logistics, think coordinating troop movements and supply chains globally, managing large satellite constellations, and swarm robotics, where you have lots of simple robots working together.
So ensuring potentially trillions of components, whether they're virtual players or real-world energy collectors, can operate together smoothly without some central point of failure bringing the whole thing down.
That's the challenge, managing decentralized complexity. And finally, the fifth area,
Which is
cycles and systems. This is all about sustainability and closing loops.
making sure things don't run out or drown in waste.
Precisely. It connects insights from ecology, how natural ecosystems recycle everything, with industrial ecology and manufacturing, life support systems needed for closed space habitats, and the principles of circular economies where waste from one process becomes feedstock for another.
Essential for long-term space presence or massive Type 2 infrastructure where you can't just keep shipping supplies from Earth.
Absolutely critical. Everything needs to be recycled and self-sustaining.
Yeah.
So these 5 specialized core of PRAs become like dedicated, trained synapses in humanity's collective brain, constantly looking for and generating these potentially world-changing cross-domain analogies.
Yep.
Okay, so we have the pattern recognition core, identifying potential connections. Now we need the actual mechanism, the engine that turns those potential connections into validated, usable breakthroughs.
Right, moving from, hey, this looks similar to, wow, this actually works.
Exactly. And the protocol lays out a systematic 5-step process. It's designed to function like a knowledge assembly line.
Contrasting with the usual sort of random scattershot approach to discovery.
Very much so. This is about methodology and throughput. Step 1 is extract.
What gets extracted?
This is where AI systems play a big role initially. They continuously scan thousands upon thousands of new technical papers, patent filings, industrial process reports, engineering blogs, everything from all over the world. They're programmed to pull out the key problems being discussed and the solutions being proposed, even if they're buried in dense technical jargon.
Okay, so the AI flags the raw data, then comes the human touch.
Yes, step 2, simplify. This is crucial. This is where the trained pattern recognition assistants and also dedicated specialists called translators jump in. Their job is to take that extracted, jargon-heavy text and convert it into clear, simple, universally understandable concepts.
So back to the fusion example.
Instead of investigating MHD instabilities, limiting plasma confinement duration, it becomes something like, problem, hot gas keeps escaping the magnetic bottle too quickly. Or, goal, find ways to keep super hot gas stable inside a container for longer.
Using plain language opens it up.
It makes the core problem visible to people, completely outside that specific field. That simplification is the absolute key to unlocking the whole cross-domain matching process.
Which leads to step 3, match.
Right. Now that the problems and potential solution concepts are in this simplified, standardized format, the pattern recognition assistants, using their specialized training, heat, flow, materials, etc., can effectively search for structural similarities.
So A PRA specializing in pressure and flow might see the simplified fusion confinement problem and say,
Hey, the pattern of keeping unstable stuff contained under pressure looks really similar to this problem we logged from deep-sea drilling,
"Hmm,
about preventing pipeline buckling under shifting pressure. They make the potential match based on the analogous structure of the problem.
okay, but lots of those matches might be, well, duds, right. Superficially similar, but physically nonsensical."
Absolutely. Many, probably most, will be dead ends. Which brings us to step 4, validate.
This is where the experts come back in.
Exactly. The deep subject matter experts, the PhD physicists, the senior chemical engineers, the veteran material scientists, they are brought back into the loop here. They receive these potential connections identified by the PRAs
And their job is to filter.
quickly,
Yeah.
efficiently. The idea isn't for them to spend weeks investigating every suggestion. It's for them to use their deep knowledge for a rapid assessment. Maybe 5–10 minutes to look at the proposed connection and say, interesting analogy might be something there. Or, no, that violates fundamental physics. Or, that ignores these critical scaling factors.
So their expert time is used very efficiently just for that crucial validation step.
That 5 minutes of expert validation could save a research team 5 years chasing a flawed analogy. It's high leverage filtering.
Okay, makes sense. And the final step, which you highlighted as really different from typical R&D.
Step 5, document. And this is critical.
Ah.
The system meticulously archives both the successes, the connections that were validated and led to breakthroughs, and the failures.
The failures, too. Why is that so important?
Because the failure archive is potentially just as valuable as the success archive. Think about traditional science or corporate R&D. How often do companies or labs spend millions, waste years, going down a path that someone else already tried and found didn't work?
Happens all the time, but those negative results often don't get published or shared widely.
Exactly. It's seen as proprietary or just not exciting enough for a journal.
Hmm.
So billions of dollars, countless years of effort are wasted globally because we keep repeating each other's mistakes in secret. By systematically documenting every connection attempt, especially the failed ones, and making that archive open,
You prevent the whole world from making the same mistake again.
you eliminate false paths systematically. That in itself is a massive accelerator for progress.
Okay, the contrast in output seems potentially huge. Traditional discovery, maybe one big accidental breakthrough per field per year, if you're lucky.
Right? It relies on serendipity. The protocol's approach flips that. It's about volume and velocity, processing potentially thousands of problems and solutions daily, generating maybe hundreds of potential pattern matches.
Even if most fail validation.
Even if 99% fail, that remaining 1% that gets validated could still represent dozens of genuine, actionable breakthrough insights emerging every year across multiple fields simultaneously. That sheer volume changes the entire timeline for innovation. Discovery stops being a waiting game and starts looking like a systematic pipeline.
And this system isn't just crunching academic papers, is it? There's this other part, the knowledge harvesting network, aimed at capturing practical knowledge.
Yes, this is vital. Because so much crucial knowledge isn't in formal publications. It's trapped in people's heads or on factory floors. So one part is problem harvesting.
Going out and finding problems.
Actively going to factory managers, workshop technicians, field engineers, and asking, what breaks? What limits your process? What are you actually struggling with day to day? And documenting those real-world challenges in plain, practical language. A machinist's struggle with tool vibration might hold the key to stabilizing a delicate satellite component.
And the flip side of harvesting problems is mining solutions.
Solution mining, exactly. Specifically targeting retiring experts. People with 30, 40, 50 years of hands-on experience.
Before that knowledge just walks out the door.
Before it's lost forever. Think of that master welder who has an intuitive trick for achieving a perfect join on a tricky alloy under difficult conditions. Something they do every day, maybe can't even explain scientifically, but it works.
That trick might be based on some physical principle that solves a problem in a completely different field, like aerospace materials.
Precisely. So then a network involves systematically interviewing these retiring experts, capturing not just their formal knowledge, but their heuristics, their rules of thumb, their tricks of the trade. Digitizing that practical wisdom and feeding it into the connection engine.
Wow. Okay, so all this effort, the pattern matching, the validation, the harvesting, it's all focused on cracking specific major roadblocks, right? The 3 critical bottlenecks.
Yes, the protocol identifies 3 huge, interdependent technical walls that if we could break through them, would likely trigger a cascade of progress towards Type 2 capabilities.
What's bottleneck number one?
Fusion plasma confinement. We can initiate fusion reactions, but we can't yet sustain them long enough, stably enough, to get significantly more energy out than we put in. Solving this is the key to unlocking truly clean, virtually unlimited energy.
Okay, bottleneck two.
Carbon nanotube strength, or equivalent material. As we discussed, the current inability to mass-produce materials with that necessary 63-plus GPa tensile strength. This blocks the development of large-scale space infrastructure like elevators, orbital rings, maybe even the structures needed for Dyson swarms.
And the third one?
Self-replicating systems. Basically, the lack of fully autonomous, closed-loop manufacturing systems. Robots in factories that can mine resources off Earth, process them, and build more robots in factories, including copies of themselves, without needing constant shipments of complex components from Earth.
Von Neumann machines, essentially.
Pretty much. We need that for exponential expansion and construction in space.
And why are these three so pivotal? Why focus laser-like on them?
Because they're interconnected in a really powerful way. Solving one dramatically helps solve the others. It creates a connection cascade. Well, solve fusion. Bottleneck one. Suddenly you have abundant, cheap, clean energy. What can you do with that? You can power the incredibly energy-intensive processes potentially needed to manufacture super strong carbon nanotubes at scale, solving bottleneck two.
Ah, okay. Energy enables materials.
Right. And both abundant energy and advanced materials are needed to build and operate complex, autonomous, self-replicating robotic systems, solving bottleneck three. And those self-replicating systems can then build more fusion reactors and more material factories. You see the positive feedback loop.
It becomes exponential. Cracking just one of those unlocks the others much faster.
Exactly. Progress feeds on itself once you break through one of these key log jams. That's why they're the focus. Now, managing this colossal global effort, tracking progress on all these fronts, keeping everyone pulling in the same direction, that requires a map. A really good map.
And that's the Type 2 knowledge tree, humanity's interactive roadmap, they call it.
Precisely. And it's envisioned not just as some static chart on a wall. It's meant to be a living, breathing, constantly updated interactive map.
Showing real progress, not just estimates.
Real percentage progress toward key milestones needed for Type 2. And the visual design is key, using color coding for instant understanding.
How does the color coding work?
Each node on this vast tree represents a specific technology, a scientific problem, or a capability needed. You click on a node, it shows you the current status, why it's important. Key bottlenecks, areas where progress is stuck and needs urgent attention, are flagged in bright red.
So you can see where the roadblocks are immediately.
Exactly. Verified breakthroughs, validated solutions, or major advancements are highlighted in green. Cause for celebration, shows progress. And crucially, every single node, red or green or in between, details specific contribution opportunities.
Ways for people to actually plug in and help.
Yes. What specific problem needs solving? What kind of pattern recognition is needed? Is there a need for solution mining in a particular industry related to this node? It turns the map from just information into an active coordination tool.
Which ties back to the whole democratized nature of this protocol. It keeps emphasizing that you don't necessarily need advanced degrees. That pattern recognition is the key superpower.
Right.
And it outlines specific roles people can play, ways anyone can contribute. There were 6 roles.
Yes, 6 distinct ways people can fit into this collective brain based on their skills and interests, not necessarily their formal credentials. Let's quickly define them so listeners can maybe see where they might fit.
Okay, number 1.
First, the pattern recognizer. This is the core role we've talked about a lot. The trained generalist who sees those structural, functional, visual connections across totally different fields.
Yeah.
The professional analogist.
Second.
The problem harvester. This person is invaluable because they often work inside industry or on the ground. They know what actually breaks down, what fails under pressure, what limits production or performance in the real world. They bring those practical, often undocumented problems into the system.
The problems that academics might not even know exist.
Exactly. Third, the solution miner. The flip side, this is someone with deep hands-on practical expertise. The veteran welder, the master machinist, the experienced chef, the innovative farmer, the clever mechanic.
The person whose common sense fix in their field might actually be revolutionary elsewhere.
Precisely. Their everyday trick could unlock a multi-billion-dollar research problem. Fourth role, the translator.
Making complexity simple.
Essential. These individuals specialize in taking dense, jargon-filled technical concepts and making them accessible, translating them into those clear, plain-language descriptions that the pattern recognizers can work with. Every concept they simplify potentially enables hundreds of new connections.
Role.
The validator.
Yeah.
This is where the deep traditional expertise is critical. The seasoned scientists and engineers who provide that rapid filtering of the connections proposed by the PRAs. They separate the genuinely brilliant insights from the well-intentioned but physically impossible ideas.
Protecting the system's resources and focus.
Absolutely. And finally, sixth, the documenter. Often overlooked, but vital.
The librarians of the revolution.
Kind of. They organize the flood of information, preserve the insights, meticulously tag everything so it's searchable, and crucially, they maintain that comprehensive failure archive. They ensure no knowledge, successful or failed, gets lost, and that the collective learns from all its experiences.
And the key point is, for several of those roles, problem harvester, solution miner, maybe even pattern recognizer or translator, you don't necessarily need a PhD.
Not at all. You need curiosity, observational skills, practical experience, or communication ability. Trained observation is the superpower.
Okay, before we wrap up, we absolutely have to hit the skepticism angle. Because this sounds, well, ambitious, maybe even utopian to some.
Understandably so.
If this systematic connection approach is so powerful, why hasn't something like it really taken off before? The protocol tackles some common objections head-on in its FAQ section, right?
It does. It anticipates the pushback.
For instance, the big one. How can non-experts realistically contribute meaningful solutions to hyper-specialized problems like fusion energy or quantum computing? Isn't that just naive?
The protocol's answer goes back to cognitive science. Experts are brilliant at depth, at precision within their silo. But that very depth can create cognitive blind spots. They can miss obvious patterns that an outsider, unburdened by the expert way of seeing things, might spot immediately.
So the welder looking at the plasma.
The welder doesn't need to calculate the magnetic field geometry of a tokamak. They just need to recognize the behavior of extremely hot, pressurized gas interacting with a metal surface under specific thermal stresses. They see the phenomenon and can say, hey, when I see that happen in my arc welder, this is what I do. We're not replacing expertise. We're building a structured way to feed outside perspectives to the experts. Cross-pollination.
Okay, what about the efficiency concern? Won't the system just generate mountains and mountains of useless random connections? A 99% failure rate sounds like a colossal waste of time and effort.
The protocol owns this. Yes, absolutely. The vast majority, maybe 99% of the initial pattern matches, will fail validation. They'll be duds.
So why do it?
Because of the scale and the documentation. First, the system is designed for massive throughput. Processing thousands of possibilities daily means that even a 1% success rate translates into a huge number of validated, potentially game-changing breakthroughs flowing constantly. Volume overcomes the low hit rate.
And the failures aren't wasted.
Exactly. That's the second point. Systematically documenting the 99% that fail is itself incredibly valuable progress. Unlike traditional siloed research where failures are hidden or lost, here, every documented failure tells the entire global community, don't waste your time going down this specific dead end. That shared knowledge of what doesn't work accelerates everyone towards what does. Failure becomes open source learning.
Okay, and the final critique, maybe the philosophical one. This whole systematic assembly line approach to discovery, it just sounds too simple, too mechanical. Breakthroughs require genius, intuition, serendipity.
The response here points to the proven power of large-scale, decentralized, open systems that rely on simple rules executed by many participants. Think about Wikipedia.
Right, an encyclopedia written by amateurs. Sounded crazy at first.
Exactly. Or Linux, a world-class operating system running critical infrastructure globally, largely built by volunteers coordinating online. The power isn't in some top-down complex master plan. The power of the Stellar Advancement Protocol, like those examples, lies in the emergent results of connecting vast amounts of distributed knowledge and effort through a well-defined, relatively simple, systematic process. Connection, at scale, is the superpower, not inherent complexity.
Okay, so let's try and synthesize this whole argument. If we boil it down, the claim is that the path to becoming a Type 2 civilization, to ending scarcity, isn't really blocked because we're missing some fundamentally new piece of physics we haven't discovered yet.
Not primarily, no.
It's blocked because the knowledge, the solutions, the insights we already have are fragmented. They're trapped in separate disciplinary boxes, locked behind jargon, unable to connect.
We have all the pieces to the puzzle, essentially. They're just scattered across thousands of different tables, and nobody's systematically trying to fit them together.
And this protocol is the blueprint for building the machine, the collective corpus callosum, to finally start connecting those pieces deliberately.
Right. And the choice humanity faces now, according to the document, is pretty stark and pretty urgent. Will the breakthroughs needed for Type 2 happen out in the open, accelerated by a collaborative, systematic, open-source approach like this protocol?
Or,
Or will they happen slowly, perhaps decades later, locked away inside proprietary corporate vaults or massive, secretive national programs? The source material explicitly mentions things like China's reported $1 trillion state-backed fusion program as the kind of closed, proprietary counterpoint.
so it's open and accelerated, or closed and potentially much slower, benefiting fewer people.
That's the dilemma framed. This protocol is essentially trying to build the engine to make critical breakthroughs inevitable, widely shared, and accessible to everyone, rather than just accidental, sporadic, or tightly controlled.
It's a shift from waiting passively for individual genius to strike in some isolated lab.
To actively building the global infrastructure for our collective human intelligence to function as a single, coordinated, problem-solving entity.
Recognizing that the solution a glassblower figured out yesterday might be exactly what a fusion researcher is stuck on today.
Absolutely. It's about truly grasping the profound, almost magical power of cross-domain connection. That insight that seems completely obvious or mundane to you in your field, your job, your hobby.
The way you solve a logistics problem, manage heat in your kitchen, fix your car.
That insight, translated and connected through a system like this, could be the missing piece that unlocks something completely unexpected. It might cascade into breakthroughs we can barely even imagine right now.
Fundamentally changing our relationship with the universe, transforming the stars from just distant points of light into eventually a power source we can actually tap into.
The knowledge is out there. The potential is latent. The universe arguably isn't the bottleneck. We are. Or rather, our lack of connection is.
So the final thought for you, listening.
The critical question this protocol leaves us with is, what pattern, unique to your experience, your knowledge, your perspective, will you recognize today? And how can we connect it?